One of the questions that people always have about Genesis is God made the stars on the fourth day, so it implies that God brought the light from those very distant galaxies far away. But I like to ask people, if the cosmos is so young, and this usually comes after much evidence that the world is young, if the cosmos is so young, how can we see so much of it? Because the most distant galaxy that the Hubble Space Telescope can see is 14 to 16 billion light years away, and maybe further. But the question is, if that galaxy that's on the screen had started emitting its light only 6,000 years ago, then you would think the light would have only traveled a short distance from that galaxy, 6,000 light years, and would not have arrived yet. So if light traveled those 14 billion light years worth of distance at today's speed, would it have had time to get here? And my suggestion is the key part of that question is the word time. The theory that I'm presenting does start from a biblical basis. The Bible plus Einstein's theory of relativity requires different clock rates in different parts of the universe. If we have the Earth near the center of the universe, and by the way, that's not something we should assume casually, that there is a center, but if there is a center and the Earth is near it, clocks would tick slower near the center of the universe, and I propose that they were ticking very much slower on the fourth day of creation. So while one day of time elapsed out on the Earth, if you could have seen what was happening in the distant cosmos, it would look like a video, and fast forward, the galaxies would be spinning and colliding with each other, and you would see, as measured by your clocks, the light just zooming in at much faster than 186,000 miles a second. What relativity demands is that when you talk about the age of something, you have to specify whose clocks you're using and where those clocks are. You can't imagine time ticking at the same rate everywhere in the universe.
So let's discuss some of the experimental support for this reality. This is not just theory. It's not. Right. It's something that has to be folded in to our right. engineering models for them to work correctly. Yes. The GPS system requires this effect to be taken into account.
There's a good book, by the way, I don't know if you've read it, John, by Clifford Will. He's an expert in relativity, one of the editors of Physical Review. The book is written for laymen, and the title of the book is Was Einstein Right? And he has a lot of the newer tests of Einstein's theory, including the tests of these different kinds of time dilation. I think people have a difficult time grappling with the idea that time doesn't tick at the same rate everywhere. And when we say time ticking at the same rate, we mean physical processes moving at the same rate. When we talk about time, we're talking about how physical processes that we would measure time with move.
Define what time is from a physicist's point of view.
Einstein said time is what clocks measure. But I like Richard Feynman, I think, said this. He said, time is God's way of preventing everything from happening all at once.
The definition I picked up is that there are things that happen in sequence. Right. And time means the sequential ordering of states of the universe.
And we found various things that agree, like hourglasses and watches that tick and the rotation of the Earth. In fact, God set up a lot of these processes so we could mark off days and years and signs and seasons, as it says in Genesis 1. He wanted us to have regular measurements of time.
If there were no time, it would represent a cessation of this sequence of states. It would be a frozen universe.
And the reason most people think that time ticks at the same rate everywhere is because it pretty much does on Earth. The difference between atomic clocks at sea level and atomic clocks at 1 mile altitude is only 5 millionths of a second per year, which is much better than our watches, but clearly discernible with atomic clocks. But to the ordinary person, time pretty much ticks at the same rate everywhere. 5 microseconds per year in a 1 mile altitude difference is not much, but it does matter when you start getting much bigger altitude differences, such as billions of light years. The creationist theory I'm talking about starts from a biblical basis. There's a simple implication of the Bible, and I talk about all of this in Appendix B of Starlight and Time. But this biblical assumption gives a completely different cosmology than the ordinary cosmology that people are familiar with, the Big Bang. And contrariwise, the Big Bang theory uses a non-biblical assumption. It's one that actually contradicts the Bible. This is the basic problem with the Big Bang. Big Bang theories assume from the very start that the cosmos is the same everywhere. And this is a quote from Stephen Hawking's book, The Large-Scale Structure of Space-Time. And in the book, George Ellis and Stephen Hawking start off their section on cosmology by saying our position in space is not specially distinguished in any way. Our position meaning the Earth's position. Then they go on and say this assumption, it implies that the universe is approximately spatially homogeneous. A lot of people might not know what that means. It means homogenized, like homogenized milk. The universe is the same everywhere, just like the milk is the same everywhere inside the carton. And spatially means in space. So homogeneous means uniform composition throughout, and that's the assumption.
Now, I think you need to clarify that that's when you average over pretty large pieces of space.
Yes.
That clearly we have concentration of stars in galaxies.
Right.
And we even have galaxy clusters.
Right.
So we're talking about on
Really
scales big compared to galaxy clusters.
Right.
The idea is that you can go as far as you want, and you don't see any major change in the density of galaxies or the general distribution of galaxies.
You have about the same number of galaxies per cubic million light years or something like that, and you don't find big empty spaces much larger than hundreds of light years across.
And in particular, this assumption is saying that you can go as far as you want and you never encounter an end to the galaxies.
Exactly. And everybody who studies cosmology sees that assumption, but the implications don't strike home. When it says spatially homogeneous, that means homogeneous in space, uniform composition throughout all space. That means there is no big empty space beyond all the galaxies. And that has important implications. This principle was extremely important, and yet it sort of sneaks in and not many people think about it. Like you were saying, John, the Copernican principle or the cosmological principle claims that the universe has no edge or center. And I've shown a picture of what I would call an island universe, or maybe an archipelago universe, where all the galaxies are in sort of a large sphere, and outside that there's some big empty space. People picture the Big Bang as starting in a large empty three-dimensional space from a little tiny thing that explodes out. And so the place where it explodes out from is a natural center. And beyond where the exploded stuff has reached is empty space. But that's the public's idea of the Big Bang, and that's not what the experts think about it. Here's a quote from Edward R. Harrison, a good book called Cosmology, the Science of the Universe. But he says in popular literature, the universe has a center and an edge. So that's how the public imagined it. But, he says, this is wrong. It has no center and edge. You might take that picture of an island universe and peel off the word Big Bang from it and call it Humphreys' crazy cosmology. But I think it's also the biblical cosmology. It's a bit hard to understand how the Big Bang experts actually look at their own theory. But in the experts' Big Bang, this is a good way to think about it. Let's say, pick a direction, and let's go infinitely fast and infinitely far in that direction. What the Big Bang assumption says is that we will never encounter a big empty space where there are no galaxies. Or even at the very beginning, we would never find an empty space with no matter and energy.
Even at the instant of the Big Bang,
Exactly.
you could find no place where there wasn't
Exactly.
matter.
Exactly.
And that is a crucial assumption,
Right.
of absolutely essential assumption behind the
Yeah.
Big Bang.
And yet the experts don't explain this because it's very hard. But this way of picturing it, if you travel infinitely fast and infinitely far, even at the very beginning, you'll never find an edge of matter or an edge of energy. So if you can't find an edge, you can't draw a boundary around it and define a volume where the stuff is, and then you can't define a center to that volume. So it has no center either, even at the very beginning. Now, quick way of explaining that is that the Big Bang assumes that our space that we exist in expanded right along with the matter. Now that's still hard to understand, and unless we talk about an extra dimension, such as the video Starlight and Time talks about, most people won't understand it. But the experts know this is hard for most people to understand, so they don't bother explaining it. But this is the crucial difference between my cosmology and the Big Bang. Why would the experts make such a hard thing to understand? Is it required by the facts of science? And the answer is no. It results from assuming the Copernican principle or the cosmological principle. This principle is arbitrary and evolutionary. And again, this book by Hawking and Ellis, in that same section, introduces it practically with this sentence: however, we are not able to make cosmological models without some admixture of ideology. Admixture means something inserted into, and ideology means a body of ideas that people assume are true without investigation. In other words, you can't just start from the observed facts about the cosmos and build a unique cosmological theory. You have to stick in some other ideas. Now, another article about this principle was written by Richard Gott in the British science journal Nature in 1993. And in this article, which was titled The Copernican Principle, he said that he started off by talking about Darwin, and he said Darwin showed that in terms of origin, we humans are not privileged above other species. We're not privileged in time. Other species were before us, and other species will be after us, and we're just the latest in a long sequence of living things. Then he says, well, the universe doesn't have very many special places, like a center or an edge. There are only a few special places. And he says in astronomy, this Copernican principle works because, why? You're likely to be in a non-special place. There's only a few special places, and if we got where we are by accident, then we are likely to be in a non-special place. Now, the problem that the theorists were trying to grapple with is that we do look like we're in a special place in the universe. The universe looks pretty much the same on all sides of us. So if we were at a center, then we would be at a special place. So they wanted a theory that would have no special places, where every place would look just like it is here.
Let's make sure everybody is following what you said. It is a fact that space, from our vantage point, looks more or less the same, regardless of what direction we point our telescopes. Is that true?
That's exactly right. And the microwave radiation that we get is very much the same from all directions.
And so there's two main possibilities. One is that we're near the center of the universe. That would, I mean, if we were near the center, things would tend to look the same in all directions.
Right.
The other possibility is that there is no center, and things look the same regardless of where you are. The prevailing viewpoint has chosen this second understanding, this second assumption, that we're not at a special place, we're not at the center, that every place looks essentially the same.
Yeah, and essentially they're saying we are going to assume and manufacture a theory in which there is no special place like a center.
Right.
And so then every place will look like every other place, and we won't have to face up to this uncomfortable idea that maybe we're in a special, very unlikely place.
Is there any way of testing which one of these possibilities is really true?
Yes, there's some exciting new evidence that we'll talk about.
But up until recently, there hasn't been a real good way of determining which position was correct.
Right. The answer is coming out that we are near a central location. But I wanted to point out to people this word likely by Richard Gott. You are likely to be in a non-special place. What's behind that word likely? He's assuming that we got where we are by sheer accident. And that's the central assumption of materialistic, naturalistic evolution.
Rejection of a purposeful creator.
Exactly.
That has purposes behind what is.
Yes. So Christians who advocate that the Big Bang Theory happened have to realize that at its heart, it's an evolutionary theory. They are unwittingly supporting a naturalistic view of the universe because this is right at the central heart of the Big Bang Theory. The Bible contradicts this principle. In Appendix B of my book, I go through various scriptures that point out that the most straightforward view of those scriptures implies that we do live in an island universe, that out beyond the farthest galaxies there's something else, and there's some empty space, at least for a little ways, and we can define a boundary around that, and we can define a volume in which there is a center of mass. Scripture also implies that the Earth is near the center of that configuration. So there's a center, and we're near it. That's a completely different assumption than goes into the Big Bang Theory. So I thought, when I first realized this, it makes biblical and scientific sense to explore a cosmology that does have a center of mass. This is why it's important. A center makes gravity important. If you have a center, then you have large-scale patterns of gravitational force. Not very strong gravitational force, but large-scale patterns pointing toward the center of mass in an island universe.
Whereas the Big Bang, this gimmick of the cosmological principle is a convenient way to eliminate gravity. This large-scale effect of gravity completely.
Exactly. Let me explain why there's no gravity in the Big Bang kind of universe. If you get out between the galaxies in the Big Bang kind of universe, far from any galaxy, and let's count up the number of galaxies on your right hand versus the number on your left hand, they're about the same number of galaxies, no matter where you are in that universe. So the forces, the gravitational forces from the right will counterbalance the gravitational forces from the left.
So the gravity where you are is canceled.
It's essentially canceled.
Essentially zero.
Now, when you get close to a galaxy or close to a star or close to a planet, then those forces are not canceled out. But in the big picture, out between the galaxies, there is no pattern a large-scale pattern of gravitational forces pointing in any one particular direction. So as you say, John, they've designed out gravity. In the biblical cosmos, one with a center, we have gravity, and we must reckon with the effects of gravity.
I think it might be helpful for a lot of people to understand why you have variations in the strength of gravity in an island universe.
Okay, all right. Well,
geometry.
Imagine yourself out near the edge of this spherical archipelago of galaxies, and then all of the galaxies are in one direction from you,
one
toward
side
the
of
center.
you.
And there's no canceling force.
You have
on the
all
other
the
side.
mass on that side tugging at you.
Right. And so if you go,
but on your other side, where there is no mass, there is nothing tugging at you.
That's exactly right.
So there will be could be a pretty whopping gravitational attraction.
It's not really whopping, John. It's so feeble that with the size universe and density universe we have today, you couldn't measure it.
But if you go back in time, as you're about to explain when the universe was much more compact.
Well, it doesn't have to be that much more compact, and the forces are still pretty feeble.
Okay.
But what matters is the distance over which those forces persist. If it's billions of light years, it becomes important. So even feeble forces over great distances have an important effect, and the effect is on time. Now, all scientists agree that gravity affects time. There's this effect that we talked about before, gravitational time dilation. And it has to do with altitude, not so much the strength of the gravitational force, but with how much energy it takes, say, to bring this coffee cup from this table up to there. That energy enters the equations and tells you how much time difference in clocks at this table and clocks up here.
For a lot of people, what you said might not be so simple to understand, that there is an energy difference associated with this cup, depending on whether it's at this point on the table or up here.
Yes.
And to illustrate it, I don't think we will on camera, I could let go of the cup and you would see some energy expressed as the cup comes crashing into the table.
Right.
So there's definitely a difference in energy associated with the cup, depending on whether it's up here or down here.
Exactly, and that's called gravitational potential energy by the physicists. But
it's very real. It's not something imaginary.
Yes,
it's not just theoretical. It's real.
Right, and if anyone watching us doubts that, just step off a step ladder sometime, and you will feel the effects of the gravitational potential energy entering your body as you collide with the sidewalk below. Even the mass of this cup differs. If I raise this cup up to here, that cup is a tiny little bit heavier, more massive, has more mass up there because of the additional energy I put into it to raise it up there. And that difference is what makes the difference in gravitational time dilation. So the easy way to think about it is that clocks that are lower tick slower. And you can remember it that way. And then a clock that's on the top of a tall building will tick just a little faster. Now, this was predicted by Einstein's general theory of relativity a long time ago in 1916. But it's been shown by experiment many times, as we were talking about before. And a nice illustration of that is the difference of atomic clocks at sea level and at high altitude. And there's a scene from Starlight and Time, the video, that illustrates that very nicely. It matters. It's 5 microseconds per year difference between sea level and high altitude. That's been measured, and that's exactly what Einstein's theory would predict. What happens when we apply this same time dilation to the whole universe and go out 20 billion light years? That's about as far as the Hubble Space Telescope can possibly see right now. How big would the effect be? What's the difference in the rate with which clocks tick here and the rate way out there? And the answer is it's not really too big. It's only 2%. If today's cosmos is an island and about 20 billion light years in radius, then clocks here are ticking only about 2% slower than clocks way out there. So we're not going to get our 6,000 years explaining all of the universe's history that way. So that's not significant. But what about the past? Was the universe different in the past? And the answer is yes. It was probably smaller. We have scientific evidence and biblical evidence for the expansion of space and the expansion of all of the universe. Now, the scientific evidence we'll talk about later is the redshift of light from distant galaxies. The further away a galaxy is from us, the more its light is shifted toward the red end of the spectrum.
Would you consider that discovery one of the great discoveries of the 20th century?
Absolutely. It revolutionized us. Edwin Hubble found that out. And when he found out that these things that they called white nebulae, or they looked like just clouds, were actually outside the Milky Way and much further away, millions of light years away, it revolutionized our view of the universe.
Most people don't realize how revolutionary that discovery was.
Right.
It took place in around 1929.
Yes.
and it had a profound effect on the thinking of 20th century man. This is not something that's highlighted in most history books.
That's a very good point. It's the first time that we became aware of really just how big a universe is. God says, as the heavens are higher than the earth, so my thoughts are higher than your thoughts. Well, we didn't really realize how high the heavens were before, and so we didn't have a good idea of how deep and large the thoughts of God are. But He anticipated us in Scripture. He had 17 verses like this one in Isaiah, talking about God who stretches out the heavens like a curtain and spreads them out like a tent to dwell in. People think of the heavens being the stars, but really, if you go back to Genesis, the heavens are something that God created before He created the stars. So the heavens, if you look through Scripture and do a little Bible study, you find out that the heavens are essentially the space where the stars are, and often the stars are called the host of heaven. He populated this space with stars, but the space is what He's stretching out like a tent curtain.
As far as revealing the profound scientific content of the Bible, this is probably one of the best examples I know of. Something that anticipated by thousands of years, predated the discovery of other galaxies, and predated the discovery of redshift.
It's almost enough to make the hair on your head rise up when you really realize what God was saying there. It was only until the general theory of relativity came along, where you picture space itself as some kind of material that can be stretched and bent, that the possibility of expanding space itself came out, because the Big Bang Theory and general relativity has space itself, the fabric of space, if you want to call it that, being stretched out and carrying the galaxies with it. And that stretching stretches out the wavelength of light traveling through space.
And even this analogy of the heavens being like a curtain.
Exactly.
I mean, that's exactly the picture that general relativity shows or indicates.
And all of modern physics has that picture. It's not spoken of very clearly by modern physicists, but they're beating around this bush all the time, and I talk about that in Appendix B and Appendix C, that the space in which we exist, though we can't perceive it, is not empty. It's a stuff of some sort, and general relativity talks about it as being a bendable and stretchable kind of stuff. And that's how the redshifts occur in relativity. It's a stretching effect. You stretch out space. Through this space is moving light waves, and the waves themselves get stretched out in wavelength. So it's not a Doppler shift, as many people in undergraduate school learned. But when you get into grad school, as I point out here, you learn that it's space itself being stretched out which produces the redshift. All of this was to make the point that in the past the cosmos was smaller, both from the biblical evidence for stretching of space and the redshift scientific evidence. So if the cosmos was smaller, then would that have had some effect, something that we need to reckon with? And the answer is yes. When the cosmos was smaller, there would be a stage during this expansion when the clocks at the center would be very slow. And that would occur with the cosmos not being 20 billion light years in radius, but maybe 500 million light years in radius. Now that's still not real small. The galaxies wouldn't be running into each other at that point, and the forces would not be that much greater. But it works out from the equations that the forces times that distance are great enough to put the center of the cosmos at a critical point. And clocks near the center would be very slow, and other processes further out would be their normal speed. But looked at from the center, it would look like everything out there is in fast forward, like a video in fast forward. Things moving very fast, and the light moving in towards us very quickly. Of course, you wouldn't be able to see that, but if you could have, that's what it would have looked like. So I'm proposing that on the fourth day of creation, things were happening very slow here. If you'd been way out there looking back at the Earth, you would have seen nothing happening. The Earth would not be rotating, nothing would be happening on it, and things near the Earth in our solar system and the nearest few hundred to a few thousand light years around us, not much happening. So it's over a general area. And this, I'm proposing, would happen on the fourth day of creation. Most of the expansion of the universe would have happened during that time. The bottom line is, if you consider what Adam would have seen and Eve after their creation, they're looking up into the night sky, how old would we say the universe is for them? And what I'm saying is that during 6 days of ordinary days on Earth, billions of years worth of events elapsed in the distant sky. So the age of the universe when Adam and Eve saw it would be 6 days Earth Standard Time, because the time that God tells us He made the universe in is framed in our frame of reference. He defined a day in Genesis 1:5. He called the light day, and the darkness He called night, and there was evening and there was morning, one day. And further down in the fourth day of creation, He says He established the sun, moon, and stars to mark off clear periods of time as seen from the earth, days and years. So when He said in Exodus 20:11, for example, that in 6 days He made the heavens and the earth, He was using our frame of reference. I always ask audiences to practice this a little. When anyone asks you, how old is the universe? I coach them in asking, whose clocks are you talking about? Because it matters whose clocks. Relativity forces us to ask that question. But as measured by clocks on Earth, this theory says the universe would be very young. And right now, about 6,000 years. When Adam saw it, about 6 days. This gives us a way light from distant galaxies could reach us, and yet distant objects would appear to be old. Galaxies crashing into each other would have time to develop and so on. Now some of the stretching may have happened at a later time. There are hints in Scripture that there was an episode of stretching that happened during the Genesis flood. I mentioned that in my book very briefly, but I point that out to point out that maybe the events that we're seeing, the crashing of galaxies into each other and the supernovas exploding, those might be events that happen after the fall, and the stretching episode at the Genesis flood would allow us to be seeing some of this chaos and confusion that we now see in the universe. So that would resolve a theological problem that some people see. The cosmology ties into the evidence that we're now finding that God accelerated nuclear decay during the Genesis flood and possibly during early creation week. And the stretching of space, as we pointed out in the rate book that we worked on, the stretching solves other problems. It cools objects from within. It gives another way to get heat out of objects rather than the classical ways. A lot of these ideas are dovetailing. Just to emphasize that this theory follows fairly straightforwardly from the Bible. We start with an island cosmos that has a center, plug that into relativity, and we get the time dilation theory. If we use the unbounded cosmos, say Carl Sagan's cosmos as its Bible, and plug that into relativity, turn the crank, we get a Big Bang. So the difference is the assumptions, and one is biblical.
A rather very simple, clear-cut difference in the assumption.
Right.
Having to do with the geometry of the cosmos.
Exactly.
Whether it
has a center or not.
Yeah. Just that simple. Just that one difference makes a huge result in the outcome.
The real irony is that the way that most people imagine the Big Bang and the universe today is as something that does have a center of mass, and that there is some empty space out there beyond the galaxies, and so they automatically think, and they talk about the center of the universe. So what people are really thinking of is what I would say the biblical cosmos is. They are not thinking of the Big Bang.
I think it might be well to point out that most scientists, even most physicists who haven't had a lot of training in general relativity have what you're calling the layman's picture.
One of the major ironies to me is that some of the advocates of the Big Bang still don't understand that. It is a difficult point, I think, to grasp, and the average astronomer doesn't understand that about it. So we have an ironic situation where a handful of specialists who work with the Big Bang theory, the cosmologists, understand this one crucial issue, but nobody else does, except a few crazy creationists. The basics of this theory are scientifically sound. If the cosmos is an island, then it's got a center of mass and a center for gravitation to point to. Clock rates have to be different in different parts of it, says relativity. And if the cosmos has expanded, then there would have been a time in the past, if the expansion continued enough, about a factor of 40 or 50, there would have been a time in the past when clock rates must have been very different between center and edge.
Maybe even zero.
Yes, infinitely different if we divide by zero. I point out from all the science we know, these conclusions appear, at least to me, to be unavoidable. My caveat is that science is always finding out new things that it didn't know and completely upsetting the apple cart. I urge people not to hang all their hopes on my particular theory, because it's basically a scientific attempt to understand Scripture straightforwardly, but our science could be wrong.
On the other hand, there's mounting evidence that the universe does have a center, and if that's true, all these variations on the Big Bang
are purely smoke.
are all
Smoke and mirrors. I think God designed relativity to, among other things, let us see a young universe. The bottom line is this theory would suggest that clocks on Earth were very slow during the fourth day of creation, and that gives us enough time to see galaxies.